Hi, my name is John Goldsmith, and this is a short course on Visio for developers. The assumption that I'm making for anyone watching this course is that you're considering developing a Visio solution and you need to get a quick understanding of what's involved and what the main development choices are. There's a vast amount of reference and feature-specific content out there, but the supply of background concepts and the more general question of how does Visio work is, I think, harder to discover. So the following material is intentionally not positioned as a detailed how-to course, but instead as a broader coverage of how Visio works under the covers, so that you're armed with the full context of how to go about developing your Visio solution. Once you've completed the course, you should clearly understand how to work with the application and avoid some of the common pitfalls that can trip up those new to the Visio development. I've split the course into two main parts. The first focuses on structure, shape construction, and the key features of the application that mark it out as unique in the drawing application space. The second part looks at the code aspects of a solution development. What your main choices are for extensibility, understanding the object model, working with the multiple options for event handling, and finally decisions about how you deploy your solution. I wanted to keep this course focused on the core of how Visio works. So there are two areas of extensibility that I'm not going to cover. The first is Visio Services, which allows Visio drawings to be viewed within SharePoint, and the second is file construction outside of the application itself using OpenXML. These are both important areas of extensibility, but I think probably merit being a standalone course themselves. So that's where we're going. Let's get started with the first module. Whatever you're doing with Visio, there are some fundamental concepts and aspects of the application that you need to grasp to build a custom solution. These concepts provide the basis of what Visio is and how it works, and when you move on to the code module, will give you the foundation for what you'll be writing code against. So I'm going to start with how Visio is structured in terms of document types, how shapes make it onto the page, and the mechanics of what Visio is doing in the background to support this. I'll then look at the logic that occurs within shapes themselves, including the shape sheet, parametric behavior, and inheritance. From there, I'll move on to data, how data is stored in shapes, the mechanism that Visio uses to hydrate a document with data and link it to the shapes, and how a shape can change its appearance based on that data. Next, I'll talk about relationships in Visio, how you can connect, contain, and associate shapes in a way that allows you not just to see the relationships visually, but crucially to query and report on them as well. I'll finish the module by looking at layout and routing, how Visio can automatically arrange shapes within a diagram, and how 1D connectors are routed around those placed shapes. So let's get going on structure. The structure of the document-based content is broadly as follows. A Visio drawing document can contain multiple pages. Each page holds a collection of shapes, and each shape contains a set of properties that define its size, position, geometries, and formatting such as fill, line, and text. Visio is different from other drawing applications like Adobe Illustrator, as from a user perspective, you're generally reusing previously drawn shapes rather than creating each one from scratch. To support this reuse, primitive shapes can be turned into masters, and these can be stored in the drawing's document stencil. Once the shapes have been turned into a master, that master can be dragged out from the document stencil and dropped onto the page where an instance of the master is created. From here, you can save your drawing as a separate Visio document type called a stencil, and the masters can then be used across multiple documents. It's worth noting the process by which a master is transferred from a standalone stencil into a particular drawing document. Let's say you have your own custom coffee store stencil, and you drag out the espresso machine master into a drawing document. As you drop the master onto the page, Visio checks to see if the master already exists in the document stencil. If it doesn't, then a copy of the master is added to the document, and it's an instance of this local master that's finally dropped onto the page. The point to understand here is that there is no further link or relationship between the master in the standalone stencil and the instance shapes in the drawing document. And this is in contrast to the direct relationship that instance shapes have with their local masters. In fact, instance shapes inherit most of their values from their local master, and I'm going to talk more about this mechanism later on in the module. So now you've got a stencil and you understand the journey from stencil master to shapes on the page, there's one last document type that pulls everything together, and that's the template. A Visio template is created by saving a drawing document as a template type. Being a normal document, it can hold a default set of pages, contain workspace information such as window layout and a list of open docked stencils, plus other document level settings, all of which will be available in any new document that's based on the template. So that's the three main document types and how they all fit together: the stencil, the template, and the drawing document. Next we'll move on to have a look at what happens inside the shapes. The fundamental unit in Visio is, of course, the shape, and although there are many aspects to it, I think there are three main areas that are key to understanding how shapes work. Firstly, that you have complete control of all of the properties of the shape. Secondly, that you can build complex logic and behaviours within your shapes. And finally, how inheritance works between master and instance shapes. Let's start by looking at parametric behaviour. One of the key things that sets Visio apart from other diagramming applications is its ability to include logic and behaviour within the shapes themselves. Visio's shapes are said to be parametric, which means that their properties are set by individual parameters, and it's those parameters that determine the shape's appearance. For example, width, height, page position, and angle are all parameters that you can set on an individual basis. And just like Excel, you can construct complex logic to control how those parameters are evaluated. Each shape's set of properties are accessible through a spreadsheet-like environment called the shapesheet. Let's flip over to Visio and have a look at it in the application. One quick point before I go any further is that to see the shapesheet, you have to have developer mode turned on. If you can't see the developer tab in the ribbon, or a show shapesheet context menu item when you right-click on a shape, then it's not turned on. If I draw a simple rectangle on the page and open its shapesheet, you can see all of the properties divided into logical sections of cells. Each section deals with a particular area of the shape's functionality, such as size and position, and geometry, and formatting areas like line and fill format. Whether you make changes to the shape via the UI, perhaps by dragging the side handles to expand the width, by typing values into the shapesheet, or even using code, in all three cases, shapesheet cells are being written to and changed, and it's these cell values that directly control the appearance of the shape. A cell can actually contain two things, a formula and a value. For example, here are two cells being displayed in formulas view. The height doesn't contain a formula, but the width cell has a formula that will make the width of the overall shape double the size of the height. And if you swap over to the values view, you can see exactly that the width's resulting value is twice that of the height. As I mentioned, formulas follow a similar syntax to Excel, and together with cell-to-cell references that you've just seen, and a set of built-in functions, allow you to build really dynamic shapes that react to changes made either by the user or via code. So let's have a quick look at functions for a moment. Some functions are mirrors of their Excel counterparts. For example, and, if, and not allow you to build logic into your formulae. Len, left, and mid allow you to manipulate strings and text, whilst date, value, week, day, and year allow you to calculate various date-time formulae. In addition to these shared functions, Visio also provides you with a range of Visio-specific functions, such as point-along-path, setF, and themeVal. In all, there are more than 200 shapesheet functions that help you build up powerful logic within your shapes. Functions, of course, aren't just used in isolation. The other key component of a formula is cell references. Cell references, just like Excel, allow you to use the value of another cell in the evaluation of your formula, and these references introduce the concept of cell dependencies. Let's look at an example. Here are a set of cells that will see the shape's width double in size if its X position is more than halfway across the page. As you can see, the width and height cells hold references to other cells, and Visio maintains these relationships by viewing them from one of two directions. For example, the width cell has two precedents, pin X and page width. If you now look at the pin X cell, it has one dependent cell, which is width. Each cell has a collection of precedent and dependent cells, and it's using this method of cell dependence that allows a value change in one cell to trigger the re-evaluation of each cell in its dependent chain. Although you can draw primitive shapes directly onto the page, for the most part Visio uses a structure of master shapes which are instanced as they're dragged and dropped onto the page. These instance shapes inherit most of their formulas and cell values directly from the master, and it's only when the user, or some code, changes the instance shape that the affected cells become local. If you're familiar with prototypal inheritance in JavaScript, then Visio's master instance inheritance is somewhat similar, insofar as if a cell formula exists locally in an instance shape, then it's this formula that's used to calculate the value for the cell. If, on the other hand, a local formula does not exist on instance shape, then the formula from the corresponding cell in the shape's master is used instead. The main difference from the JavaScript analogy is that while a prototype can inherit from other prototypes, all the way up to object, this is not the case for Visio. A Visio master does not inherit from other masters. So let's take a look at a quick example. As you can see, I've got a master named Square, and I'm just going to drop 3 instances onto the page. I'll open the shapesheet of the middle shape, and the first thing to notice is that some of the cells are blue and some are black. Visio represents local formulas in blue and inherited ones as black, which makes it a little easier to see what's going on. For example, if you look at the height cell, you can see that this inherits its formula from its master. Let's go up to the shape and reduce this to be, say, 20 millimeters. And notice that the cell formula is now blue, indicating that it's become local to this shape instance. I'll close the shapesheet and quickly open up the master and edit the height cell. This time to say 40 millimeters. When I close the master and accept to update, the new heights are reflected in all of the instance shapes that inherit from the height cell. Now, I said earlier that masters cannot inherit from other masters, but what they can do is inherit from styles. Styles are a master-like object in Visio that can be used to apply line, fill, and text formatting to shapes, all via the inheritance mechanism. So a master can inherit from a style, and if that style only applies line formatting, for example, then it might also inherit fill and text from another style. The story doesn't end there, as styles can also inherit from other styles, and ultimately, unless otherwise specified, from a special root style named noStyle. While the individual style details aren't so important, the key thing to understand here is how on any given shape, some cells will be local and some will be inherited. And when your solution makes changes to shapes, it's better to work within this inheritance mechanism where reasonably possible. A key feature of Visio that sets it apart from other drawing applications is that it allows data to be attached to shapes. There are three main aspects to this. Firstly, there is where the data is stored. Secondly, how you get the data in and out of the shape. And finally, how you visually display the data. There's a couple of items here that I've added just so you know that they're there, but I'm not going to go into great detail as they tend to be legacy features only. So let's get going and see how data is stored in shapes. The shape sheet isn't simply for cells that affect the appearance of a shape, but it can also be used to store the data as well. Every shape sheet can hold a shape data section that contains one or more rows. The cells within a row enable you to give it a name and various attributes, such as a display label, a data type, and the value itself. Once a shape data row exists, you can not only edit and report on this data, but also reference it from other cells within your shape, which can alter the visual appearance depending on the values that exist. As you can see, changing the value in prop.poweron changes the shape's fill colour from green to grey, depending on the state. If you're wondering what the prop part stands for, it's because prior to 2007, shape data was called custom properties, and the prop reference still remains. While the shape data section is a great place to store logical properties of the object your shape represents, there's another shapesheet section that also allows you to add a custom collection of named rows, and that's the user section. Unlike shape data, user cells have no associated UI, but they're an excellent place to define what you might think of as local variables within your shape, and since they're nameable, have meaning when viewed in the context of a referencing cell. I want to be a little bit careful that I'm not misleading you on using the word local. There's no scoping going on here, and as long as you have the full syntax, you can reference a user cell in another shape that's sitting on a different page, but by and large they tend to get used for references within a single shape or by children of a given page or group shape. In a second, I'm going to have a look at an example of using shape data and user cells together. But before I move on, I'll quickly mention the Scratch section. The Scratch section predates both user and shape data sections. Its rows are not nameable, and so these days you'd be well advised to use user cells in almost all circumstances. One caveat to this might be where you need to calculate geometry and other 2D coordinates, since the structure lends themselves to this use. So let's have a look at an example of using the two sections together. Here's a coffee shape. It's a group shape containing three child shapes, one to represent the coffee, one for the milk, and one for the foam. A shape data row defines the type of coffee and uses a fixed list data type. The items for the list are set in the format cell, and whenever the user changes the value via the shape data window, Visio pushes a formula with an index function into the value cell, selecting one of the values in the list. A user section provides 5 calculated variables. If you ignore the details of the formulas for the moment, you can think of this as basically 3 separate parts. Firstly, there's the coffee type index, which looks up the selected value in the shape data list. There's the 3 basic ratios to determine the heights of the coffee components, and these are used by the 2 remaining point cells to give the actual XY position in the cup. Changing the coffee type shape data value sees the respective levels move up and down accordingly. Although this particular example is based around coffee, and the things we're changing are just the geometry of the subshapes, the point to emphasize is that not only can you store data in a shape, but fundamentally drive its appearance based on that data. I'm going to move on now to talk about two features that appeared in Visio 2007, link data to shapes and data graphics. Both are only available in the professional and above product editions, and this is something to bear in mind if your solution needs to work across all editions. Let's start with the first one. The data synchronization story in Visio basically works in a single direction. This is highlighted by the name of the out-of-the-box feature, which is link data to shapes. This feature has a UI and accompanying API that allows you to map data from a range of data sources to shape data rows within a shape. The basic workflow goes like this. You select a data source. This creates data connection and data record set objects. And both of these are stored in the document that you're linking to. So the final step is to create the relationships between the data record set rows and the shape data rows in one or more shapes. Beyond this basic setup, you can create multiple data record sets from multiple sources. So for example, where we've got the first SQL Server source here, you could add a second data record set connected to an Excel source, and a third record set being fed by an XML document. One quick point with the XML data source is that this is only available via code, and that being a file, it's seen as a connectionless record set. With these additional data record sets in place, you can also see other types of linked relationship. So while we're currently looking at one row to one shape, others include one row to many shapes, and many rows to one shape. This last relationship type highlights the restriction that you can only link one row from each data record set to a single shape. This makes sense, of course, because what Visio is trying to do is to map the columns in a record set to the named shape data rows in a shape, and trying to do that more than once would override the previous mapping. Before I move on to a demo for data linking, I'm going to have a quick look at data graphics, which go very much hand in hand with linked data to shapes. Data graphics is another feature that was introduced alongside linked data to shapes in 2007, and like its sibling, is also not available in the standard edition of Visio. The feature enables users to create additional, what you might describe as attribute shapes, and apply these dynamically across one or more target shapes on the page. There's a set of built-in types, and these can be applied via the UI or in code. It's also relatively simple to create new icon sets for custom data graphics. So I think it's time to have a look at a quick demo in Visio, and you can see how the linked data to shapes feature works from a user perspective. I'm going to start off in Excel, where I've managed to get hold of the basic data for menu planning at the Visio Coffee Company. These guys have seen exponential growth over the last few years, and this is all clearly down to their clever use of a range of custom Visio tools to communicate strategy throughout the business. Fortunately, they've seen my coffee cup shape that I used earlier and have asked for a single page detailing all of the coffee combinations that staff can use at checkout. So the data's pretty straightforward, and I'm going to jump into Visio to hook it up to the document. So I'll start off the wizard by selecting the workbook and the named range within it. I can then filter down the columns and rows that I'm interested in, identify the primary key, hit finish, and the data record set's created. There's a couple of ways of linking data. First, you can link data to an existing shape, in which case you just drag a data row out and drop it onto the shape. Or you can create new shapes by dropping the row or rows onto a space on the page. I'm going to choose this last option, and you'll see that as I drag out the rows, Visio uses the selected master as the shape to drop. Unfortunately, there's no grid layout, so you can either do this in code or manually, as I'll do now. Of course, with the power of video, it's not quite so painful. Good, so that's added the shapes to the page and linked each one to the corresponding row in the data record set. At this stage, let's open up the shape sheet of one of the shapes and have a look at what's happened in the shape data section. I've modified the original master shape to include 3 new rows. So in addition to prop.type, I've added prop.cupsize, prop description, and prop.price. I didn't add the product code row on purpose, as I wanted to show that Visio will add shape data rows to a shape if they don't already exist. Any rows added in this way can be identified by an underscore visdm underscore prefix, followed by the column name from the data record set. Another point to note is how Visio maps the columns to the shape data rows, which is via the label shape data cell. So you can see here that the labels for type, cup size, description and price all match the respective column headings in the data record set. So it's not the shape data row name that's used as you might expect. So the shapes are on the page and the data's linked. I'll now add the data graphics to surface the shape data visually. I'm not going to step through the construction of the data graphics, but I'll open it up in the edit dialog to get a look at all the moving parts. As you can see, this data graphic has 3 items. The first 2 are text type, and the third is a data bar type. You can see the shape data rows that the items are mapped to, and you can of course change those if you like. If you open up one of the items, you can see a range of properties that affect its appearance. And if you create a new item, you can see that there are basically 4 different data graphic item types. Text and data bar, which you've seen, icon set, and color by value. The color by value type is different from the others in that text, data bar and icon set all add additional shapes around the target, whereas color by value actually changes its fill color. So that's a very brief introduction to link data to shapes and data graphics. In the meantime, this completes the data part of Visio. You've seen where data can be stored within shapes, how data can be read and mapped to shapes, and also how you can apply additional graphics based on that data. In the final part of this module, I'm going to look at the different ways that Visio uses relationships within diagrams to connect and associate shapes with one another. Visual relationships can be expressed in a number of different ways. For example, by position and proximity, by colour, by connection, by containment or enclosure, by order and by association. There are many more like texture, size and of course shape, but 4 of these relationships stand out in particular when using Visio. While many drawing applications can draw 2 rectangles and a line between the 2, Visio is different in that it's able to capture the logical relationship as well as the visual one. By exposing this logical relationship, Visio allows you to read which shapes are connected to each other, or which shapes are contained by one another. This allows you to navigate through all the connections in a diagram, for example to read a hierarchy in an org chart, or to understand which process shapes sit within a particular functional swim lane. I'm going to start off by looking at connections, move on to containment and order, and finally look at association. Visio maintains connections between shapes via a system called glue. In a connected diagram, it's this glue concept that provides the logical connections between objects. Glue is created either via code or through gestures in the UI. For example, if you drag the endpoint of a 1D shape over another, Visio will highlight the places that you can glue the endpoint to. If you release the mouse button over, say, one of the 4 connection points, The connector endpoint will be glued to the target shape. You can then reposition the rectangle, and the line's endpoint will follow the same point that it was glued to. If you look at the shapesheet cells in the 1D shape, you can see what Visio is up to. As the mouse button is released, Visio fires some formulas into the endpoint cells to track a point on the target shape. In some situations, such as when you glue to shape geometry or to a shape handle, Visio dynamically adds connection points to the target shape. But aside from this, the target shape remains basically untouched. If you were to look at the cells in the target shape, you'd find that no changes have been made due to gluing. What all this highlights is that glue is not an equal relationship. There's a gluer shape and a target shape. If you subsequently move the target shape, the glue is maintained. But if you move the gluer, then the glue is broken. You can also think about this from a glue creation perspective. If you're dragging a shape towards another shape in order to create glue, then the shape that you're dragging is the gluer, and the one that you're gluing to is the target. So now you know basically what glue is, let's look at which parts of a shape can be glued to which. The most usual glue type you'll find in Visio is a 1D endpoint gluing to some part of a 2D shape. So let's start with that. Here's a slightly modified version of the rectangle we've just looked at. I've made a few changes to the geometry so that I can highlight some of the different glue pairings, and that includes a circular cutout whose position is based on a control handle that's part of the shape. There are 5 main elements that an endpoint can be glued to: selection handles, geometry paths, connection points as you've seen, shape vertices, which are the points between geometry segments, and guides, and in fact guide points as well. In addition to 1D endpoints as the gluer in the relationship, you can also glue shape control handles and connection points to the same targets as the endpoints. And on top of that, you can glue a 2D shape's alignment handles, or selection handles, to a guide. So for example, I can drag the control handle of this 2D shape and glue it to a connection point in another shape. Equally, if I drag this small 2D shape over its neighbour, I can glue the connection point in the shape that I'm dragging to the one that exists in the shape that I'm hovering over. Okay, so far what we've looked at is what's known as static glue, and that's one of the 2 glue types that are available in Visio. The other is called dynamic glue. With static glue, what you're doing is gluing a point in your source shape, or gluer, to a point in your target shape. Once this has been set up, the point in the target shape will be tracked, and you can see this happening if I move a 2D target around like this. Now contrast this with dynamic glue. If I drag the endpoint of this new line over the target shape, you can see the existing connection points that are available to glue to, and that if released when the mouse is over one of them, I'd get yet another statically glued connection. But notice that if the mouse is anywhere else in the shape, a green box highlights the entire shape, indicating that dynamic glue will be created instead. I'll do that now, and let's look at what happens when the target shape is moved. You can see that the static connections stay put, but the dynamic one tracks around the shape to find the shortest path from the edge of the shape. While dynamic glue makes sense for many situations, such as an org chart or a process diagram, in others, such as an electrical diagram, it clearly does not. This is a key decision in designing your solution. For example, if you look at these simple process shapes, beyond preferring a left to right style, you probably don't care which connection point a connector line is connected to. It's enough to know that conceptually, process A is connected to decision B. This means that dynamic glue is the right choice in this situation. On the other hand, if you look at this circuit diagram, It's clearly important that the tracks remain connected to the same points that they were originally glued to, and so static glue is the one to use here. So the concept of glue is simply the method of allowing Visio to create both visual and logical connections between shapes, and the behaviour of those connections is determined by whether they're static and stay glued to a specific point, or dynamic where they track around a shape to find the best fitting path. Next, let's move on to containment. While a line between two entities shows a relationship by connection, containment implies some form of ownership or of being part of some other entity. Prior to the 2010 version, you could display this form of relationship in Visio by either drawing a rectangle around another set of shapes, or actually grouping a set of child shapes to create a single parent. Both methods work well in many situations, but they both have their drawbacks. The rectangle method, while flexible, needs to be manually updated every time one of the target shapes are moved in or out of the containing area. In code, you could do lots of spatial queries, but you've still got to understand the intention of the user when they add, remove, or simply move one of the shapes. Also, the target shapes have no knowledge of whether they belong to the bounding rectangle or not. On the other hand, with grouping, the target shapes have a more permanent link with their parent that's really at the other end of the flexibility spectrum. Grouping is generally better suited to more static components that are part of a distinct single unit, such as the legs of a chair or the door of a vehicle. Containers, which were introduced in Visio 2010, address these shortcomings and sit in the middle of the flexibility spectrum by maintaining relationships, but crucially without altering the underlying structure. So think, for example, of employees being assigned to project teams or some other organisational unit. I've got two container shapes here, and I can select a set of employees and add them to the regional managers container. Notice that as I drag the shapes over the container, Visio displays a green rectangle around the container's edge, indicating that the shapes will become members of the container as they're dropped. Now that they've been added, I can move the container and the member shapes follow along as you'd expect. But the important thing to understand is that the structure of the shapes hasn't changed, and I can still select a single employee, move her out of the container, and the remaining member shapes are left untouched. Another key feature of containers is that member shapes can get a reference to the container that they're sitting in. So in these employee shapes, I've actually added a small circle which changes dynamically to highlight which container they're in. If I move these 4 employees into the new store openings team, you can see the circles reflect that change. I've also added a numeric text field to the container's header area to display the changing member count to show how a container shape can have knowledge of its members. What I'm trying to demonstrate with the circle example is that you've managed to change the data in an instance shape simply by allowing the user to move the shape on the page, and this is pretty powerful. As I mentioned, containers were introduced in Visio 2010 and form part of a feature called structured diagramming. This feature is made up of 3 main types, of which containers is one part. The other 2 types are lists and callouts. I'm going to talk about callouts in a minute, but first let's take a look at lists. Lists are essentially another type of container, but one where position and order are controlled. They allow you to display a list of shapes in either horizontal or vertical orientation. For example, here's a list shape that I'm going to use to show the order of responsibility for closing a particular coffee store at night. If I drag the managers into the list, you can see that Visio again displays the green line around the outside of the list to show that the shapes will become members of the list as I drop them. You can also see that if I want to reorder the list, Visio provides me with the associated UI elements to allow me to do that. The way that containers and lists work is based on a set of diagramming services running in Visio that look out for shapes with a particular set of named user cells. If you look at the shapesheet for this list shape, for example, you can see that there are a number of cells named user.msv and then some following name. Let's have a look at the most important ones. Structure type identifies this shape as a structured diagramming list type. If this were a container or a callout, the value would be those names instead. The next cell to look at is shape categories, which is a cell that can be applied to any shape and allows you to effectively tag shapes as belonging to a particular category. This in turn can be used with an inclusive or exclusive filter, such as SD list required categories, the SD being structured diagramming, to allow or prevent item shapes of a particular category being added to this list. So in this example, I've already set the shape category cell in each of the employee shapes to be either manager or staff. As you can see, this list has a requirement that only items with a shape category of manager will be allowed to be added to this list, and if I try and drop one of the staff shapes onto the list, Visio won't display any of the green outline UI or adopt it as a member shape. All of the other cells just identify other aspects of the list, such as styling or layout, and sync with the contextual ribbon tab to enable the user to set the varying options. So the user cells identify a shape as being of interest to diagramming services and store all of the attributes about the shape, but there's one more cell that's used to complete the feature. Further down the shape sheet, in the shape layout section, you'll find the relationships cell. Visio uses this cell to store the relationships between one shape and another. So for a list or container shape, like the one here, it will store a reference for each of the member shapes. And if you open up the shape sheet for one of the member shapes, you can see the corresponding reference back to its container. Although you should never need to interact with the relationship cell, it highlights the bidirectional link between the shapes and how Visio maintains these relationships in the background. Before I finish the discussion on relationships and structured diagramming, I'm going to quickly touch on callouts. Callouts provide an associative relationship that allows you to tie the position of one shape to another, and like containers, without grouping or any change in the structure of either the target shape or the callout itself. Here's the store lockup list again. I can drop a built-in callout shape on the page, associate it with one of the manager shapes using the control handle, and then make a note that this person is only available on weekdays. I can then move the target manager shape, and you can see the callout following along with it. This is a pretty standard scenario for callouts, using them to annotate or highlight another shape in the diagram. But you're not stuck with just displaying the text or only using the built-in types. Here's another custom shape that I've added callout behavior to. I can associate this key shape with another of the manager shapes to show who currently holds the keys to the store. Again, I can shift the order about, but the callout remains associated with the same target manager. I can easily move the key to another manager, and the key will now track the new target. So that's just about it for relationships in Visio. I've looked at quite a bit in a short space of time, but the key takeaways here are that Visio supports a number of different methods that allow you to capture the logical relationships that your users construct as they assemble a diagram. They haven't done this by mapping one text field to another, but by visually moving the objects that make sense to them and the domain that they operate in. Another significant feature is Visio's ability to lay out the shapes on a page, using not only basic alignment, but also taking any connected relationships that exist into account. For example, I'll drop a group of simple shapes onto the page like this. I'll number them, but only to make it easy to see the hierarchy that I'll create as I add the connections. I'll add the connections now and set the root node to green for clarity. Because of the from-to nature of connections, Visio is able to interpret the hierarchy so that when I change the layout style to one of the built-in items, you can see the effect that it has on the arrangement of the shapes. To enable layout, Visio makes a distinction between two types of shape: a placeable shape and a routable shape. Placeable shapes are shapes that, as you can imagine, can be placed or arranged across a page. Routable shapes, on the other hand, are shapes that can be routed around those placed shapes. Placeable shapes tend to be 2D shapes and routable ones 1D, although not all 2D shapes are necessarily placeable, and likewise not all 1D shapes are routable. Of course, as with most things in Visio, there's an accompanying cell in the shapesheet, and in this case, it's one named ObjType that determines what type it is. When you're designing your shapes, you can decide whether you want your shape to be placeable, such as a flowchart node, or where you want to opt out of layout behavior, perhaps for a shape that represents a pillar or a wall in a building. In general, new primitive shapes that you draw on the page are set to let Visio decide on what type it should be. Under these circumstances, a shape will only become placeable if you connect a connector to it. All of the built-in layout and routing styles can, of course, be applied through the UI, but ultimately the settings that determine the behavior are all stored in the shapesheet at both page and shape levels. These shapesheet sections reveal a couple of interesting details. Firstly, there's the plow cells. These cells introduce the concept that Visio allows shapes to push or plow other shapes out of the way if they're positioned on top of them. The combination of shape plow code and shape fixed code determines whether a shape can plow or be plowed, and allows you as the shape designer to control whether you opt in or out of this behavior. If you're wondering where you might use this type of functionality, then one example might be the coffee store floor plan, where as you drop a table shape onto the page, it makes sense that one table shouldn't cover or overlap another one, and ploughing ensures that this doesn't happen. The second set of cells to point out are the block and avenue size ones. Visio uses these cells when it calculates the spacing for the layout styles. As you can imagine, avenue size is used for the space between shapes, while block size is used for the space given for each shape. Of course, the actual shape sizes may vary from the block size values, and so additional logic is applied to the final result. So that's a quick overview of layout and routing. I want to emphasize two things. A, that Visio has a number of layout algorithms that your solution can hook into, and access to these is available for your users via the UI or to you via methods in the API. And that B, there is a reasonable level of fine detail control to get you the style that suits your solution. Of course, there's nothing to stop you creating your own logic if the built-in ones don't meet your needs, but it's definitely worth taking a look at what's in the box first of all. So we've covered quite a lot in this module. There's been a fair bit of detail and perhaps some formulas that you weren't familiar with, but the purpose of the module is to lay a foundation of the main concepts within Visio, and I want to highlight them once more. I started off with structure, and we looked at how a shape in Visio is normally an instance of a master. One or more masters live in a stencil document and are copied to the drawing's local document stencil, where they're instanced or dropped onto the page. Each shape has a backing properties page called the shapesheet, where you can define logic and expressions to control virtually all aspects of the shape's appearance. You'll come back to the shapesheet a lot, as it's these cells that you'll be writing to when you move on to the code module. In terms of data, you saw that a document can hold data record sets, and that rows can be mapped to each shape's local data store called shape data. We looked at relationships and how you can interrogate the logical connections between shapes that your users create. And finally, you saw how Visio contains a range of built-in layout and routing services, allowing your users to control layout themselves and freeing you from writing what can become quite complex layout logic. So now that you understand how Visio is structured, it's time to look at how you access the same documents, pages and shapes in code.